All right. Thank you, everyone, for joining the April edition of the Ice Giant System Seminar Series. We took last month off for the Lunar Planetary Science Conference, but we're back at it. We're going to have a couple of speakers coming up in the next few months that I'm very excited about. Today, we have Matthew Belyakov here to talk to us about JWST spectroscopy of the small satellites of the ice giants. Before we get started, I just want to remind you, if you haven't signed up for the listserv to get information about upcoming seminars, you can at the link that I dropped into the chat. All of the information about upcoming seminars are on there, and we try to update it as soon as we have information on those upcoming speakers. So what we'll do today is Matthew will give his presentation. He said he can take questions during his talk, but feel free to put your questions in the chat or raise your hand and I will call on you. And we'll have a short period of time at the end for questions. And then at the very end, we have a little bit of a community news segment that Jody will go through all of the relevant job postings, meetings coming up that are relevant to the Ice Giants community. So without further ado, I'd like to introduce Matthew Belyakov. He's a fourth-year graduate student at Caltech, working on small bodies in the outer solar system. He's combining dynamical and spectroscopic studies of the Kuiper Belt, irregular satellites, and the small inner satellites and rings of the giant planets to try and constrain early solar system evolution. So without further ado, take it away, Matthew.
Thank you. It's my pleasure to be giving this Ice Giant seminar today. And what I want to do is try and walk you through some of these latest results me and my co-author Riley have obtained on these small moons you see on the left and right side of the screen here that are feeding the rings of Uranus and Neptune. So for Proteus and Puck, these are the best images we've had, and we haven't had very much data on them since Voyager 2 flew by. So James Webb is really the first time we're seeing these in a totally new light. And hopefully I'll convince you that these moons are pretty important in understanding the history of our ice giant systems and really their satellite systems. So what I want to first do is most of the audience here is very familiar, but just review briefly what are the important components of the system architecture when thinking about these small moons that are on very totally circular, almost totally circular, and almost totally uninclined orbits. There are a few that are in these high order mean motion or inclination resonances, but really they're all pretty aligned with the equatorial plane of these ice giant planets. So these are the two beautiful NIRCam images we have of the two systems. And the first thing that stands out to me is the axial tilts of the systems. So for Uranus, we have the 97.8-degree axial tilt, which is indicative perhaps of some early collisional history, some violent disruption. And there are authors that claim that maybe two collisions even happened to tilt the system. And what that could imply is the destruction of the original regular satellite system, and that what we're seeing here is some second, perhaps even third generation of satellites that formed out of a disk that was created subsequent to the collision with Uranus. So perhaps what we're seeing is not quite the original satellite system, and we need to keep that in mind when we're thinking about all these 13 small satellites right next to Uranus. And yeah, there are the 5 here main regular satellites of Uranus. They're in hydrostatic equilibrium. Their compositions are bright. They have rich water ice, rich CO2, and Richard Cartwright is the one working on these and has probably shown at one of these seminars in the past. But if we look at Neptune, it has a much less drastic tilt that still needs to be explained, but there's more leeway to get away with tilting Neptune without necessarily having a giant collision, such as the capture of Triton. Triton is this sort of collection of all the mass in the satellite system, right? It's 99 point something percent of the mass in the satellite system. So what happened is early in the history of Neptune, you have an encounter with a Pluto-like body. Triton is pretty similar in its composition, size, parameters to Pluto. And you have Triton with its original moon, something like a Pluto-Charon pair, and the Charon in that pair gets kicked out and the Triton gets captured. And this capture will destroy whatever was there in the regular satellite system. You could have all these satellites hit each other, all the regular satellites that are originally there, and Triton effectively depletes the system of most of its mass. What you're left with is these seven inner satellites, which are plausibly remnants of that original system, whatever, was not ejected fully by Triton. So we have one system which looks relatively complete with this weird axial tilt, and one system which has generally been depleted. Most of the information we had originally about that system is lost. But what we do have is a collection of all these small inner moons and the ring systems, which hopefully can tell us something about what is happening with these systems, what is their early history, and how did they evolve. And this is perhaps vague, so let's just take a closer look at these moons and figure out why they're interesting, what information they store, and what we've learned from James Webb about them. So the looking at these collections of small moons and the fact that they hadn't been really looked at since Voyager is what led me and Riley to submit this proposal to James Webb to look at the collection of the small inner satellites, these sort of medium-sized 400-kilometer bodies like Proteus and Miranda, and the more distant irregular satellites, which I won't really be talking about in this talk, because we think that, when we're looking at bodies like Ariel, Triton, all of these large bodies, the geology on them is going to largely erase the sort of primordial material in the state that it was initially. And perhaps the hope is that by looking at these small bodies, this is a sort of typical argument when people discuss the Kuiper Belt, asteroids. You want to look at perhaps the smaller bodies which preserve the original collection of material that wasn't heated too much and wasn't distorted too much. That was sort of our hope in submitting this proposal, maybe to look at some of these smaller bodies and see what information we can glean out of them. And the previous spectral data was kind of sparse. We had Voyager and Hubble data. We couldn't really access the 3-micron region, as has been true of spectroscopy. In general, in the pre-James Webb era, we weren't really able to check for CO2 at 4.27 microns. We weren't really able to look at the full water band at 3 microns. And it was difficult from the ground, even where we have atmospheric transmission windows. But we did know that these are pretty, if you look at the left side here, if you look at Puck, the Portia group for Uranus, the inner satellites are generally seen as these dark neutral bodies. This was their characterization for the past 30 years. And hypothetically, there was some slight evidence that there were 2-micron features indicative of the presence of water ice, as you can see on the right panel here. So what we did initially a few years ago was to look at the photometry that's collected of those. In fact, those beautiful images from NERCAM that you saw originally were done for PR purposes, but we realized that because they were done in 4 bands, you could extract a decent first order approximation to what their spectrum looks like from the 4 band images taken. Since then, I know Matthew Hedman is working on getting much more refined photometry for the full collection of all the 13 moons of Uranus. This was just a first peek, and really the goal here was to see, okay, we have these objects, we haven't seen them since Hubble and Voyager. What do they look like? Do they have large 3-micron bands? Or will their 3-micron bands look relatively flat? And the 3-micron band is a typical tracer of OH, water ice, the sort of hydration that is typical throughout the outer solar system. And we found that the OH band looks pretty deep. They are still, dark objects, albedos of around 0.1. But the question is, how do they compare to the rest of the outer solar system? With all the spectroscopy happening with James Webb, we had all this rich data that we could use, these 4 points on all of these moons to compare to the wealth of Kuiper Belt data that we had. So in order to really look at the Kuiper Belt data, I should introduce some of it. There's been a very rich investigation of the spectra of the Kuiper Belt, these small bodies, and they really are best analog, perhaps, to what these small satellites are. Small, relatively small, 100, 200, 300 kilometer sized bodies that are full of volatiles that formed in the outer reaches of the protoplanetary disk. And so we have really established that there are three sorts of types of Kuiper Belt objects. These are the ones that are now being discussed in the literature. There's a paper by Noemi Pinella Alonso that really sets these three as the sort of prototypical Kuiper Belt object types. And at the top, you have these water-rich objects that have this 3-micron band with the Fresnel peak, and then you have these two other categories, which are the more organic rich, were often called the very red objects, things that have all these organics that are formed further out that are really dissimilar to what we see closer in. And so just to characterize some of these spectral features so that we have context for later, at 1.5 and 2 microns are the H2O overtones, the features that are truly indicative of the actual presence of water ice, not just hydration, as you see at 3 microns. Then we have the CO2 at 4.27 microns, which is present almost ubiquitously throughout the outer solar system. We see the CO2 even where you're really not supposed to see CO2 at places like the Jupiter Trojans at Euripides, places where it's way too warm. So CO2 is this common thing we've seen in the outer solar system, and it's really James Webb that has opened our eyes to the presence of common CO2. Then we have CO at 4.68 microns, and we don't see that on these water-rich objects. They have less of the organic component, and we see it on these organic-rich bodies. And finally are the aliphatic organics themselves at 3.4 microns. You see this broad sort of additional bite out of the spectrum in the orange and the red categories, the methanol rich and the CO2. I haven't actually highlighted the methanol. It's at 2.3 microns there, those sort of little absorption features. But sort of these categories of objects are the fundamental paradigm through which now we view outer solar system compositions, right? There are these things that, used to be termed either they're more blue, or sort of neutral colored, or they're more red colored. Now we actually know what those colors mean. We actually know that water-rich objects have these, blue objects are these water-rich objects, the ones that have the Fresnel peak at 3.1 microns you see. They do have a bit of CO2 and water ice, whereas the red ones are the ones that are really dominated by their organic CO2 component. And so we use this to compare our spectrophotometry for the small satellites of Uranus and Neptune, these 4 data points that we got, to the Kuiper Belt spectra. And what we saw is that the best match, really, to the small satellites of Uranus and Neptune were these water-rich Kuiper Belt objects, especially the ones that we knew had the lowest albedos from like Spitzer and Herschel measurements back in the day, like this 2004 EW95. This is a Plutino. Sits in the 2 to 3 mean motion resonance with Neptune, and it has this water-rich composition, has a bit of the CO2, has a bit of these 1.5 to 2 micron absorptions, and in its spectral slope and in the depth of the 3-micron feature, and in the sort of upswing back in the continuum towards 4.6 microns, where we have that last data point on the right, it seemed to be the best match. And so our hypothesis going in before we got the James Webb data on our small satellites was that, okay, we're going to see things that look pretty much like these bold type water-rich KBOs. And sort of that was what set our expectation. And we were thinking, okay, if this is what they look like, then perhaps you have Kuiper Belt material that is being incorporated into the rings and these small satellites, maybe due to collisions, maybe due to other processes. And so that was sort of our expectation for the data going in. So the first set of data I want to talk to you about is the inner moons of Uranus. And we got lucky here. We kind of struck gold looking at Portia. we sort of managed to actually, in our IFU, we have 7 dithers of Portia here, and the nurse spec IFU is a 3x3 arcsecond window, so it's quite small, but we managed to get 4 distinct moons here. You can actually see Portia, Juliet, the small moon Perdita, which I believe is only 13 kilometers across. Um, in the IFU, and you can't really see Cordelia. It's just too small and too blended with the very bright epsilon ring. So we really got lucky here. Puck is not in this IFU. We got another separate set of dithers on Puck. So we actually got sort of 5 moons. Well, call it 4 since we can't really extract Cordelia separately for the price of 2. So this data reduction has been a bit of a struggle because the scattered light from Uranus is quite heavy component. But for Portia, Juliet, even Perdita, and of course Puck, we've been able to extract pretty decent spectra. And this is what they look like. This is really the first full 1 to 5 micron spectra we have of these moons. And what's fascinating is 2 first order. Perdita's very noisy, but they all look pretty much the same. They all look like these water-rich KBOs, which is what we expected, is sort of our expectations confirmed. They have the 2 micron feature, well, Puck and Portia more so than, say, Juliet. They have this big 3 micron absorption. They have the Fresnel peak at 3.1 micron. That's sort of that little divot in the larger 3 micron absorption that's indicative of actual facets of water ice being exposed on the surfaces. And they all have CO2 to varying amounts. It's pretty similar. And you sort of see, I've plotted them from outermost at the top to innermost at the bottom, moving in. And the slight trend that you maybe notice is that the Fresnel peak does change between Puck and Juliet. It grows a bit more pronounced on Juliet. So perhaps there's some difference in the microphysics. Maybe Juliet as a smaller body relative to them. Maybe it has experienced a more recent collision. Portia and Juliet are associated with a faint ring. If we go back 1 slide, if you look at the image on the right, Juliet and Portia are near a faint, relatively dusty ring, indicating some sort of relatively recent collisional processing. So perhaps that more recent collisional processing has enhanced the amount of the small fine-grained water ice that is attached to the fine sort of regolith on top of these surfaces. And, more broadly, you see sort of with Juliet, it has this upwards sloping near infrared slope that Portia and Puck don't have. And if it were only the spectrum that I had here, I would not believe this detection of a difference in the slope. Maybe I'd say, okay, it's a difference in the, say, scattered light. Maybe I'm not reducing something correctly. But this is the exact same thing that I've seen in the NERCAM data for Juliet. And I'm actually curious if Matt Hedman, if you see the same sort of thing in your more up-to-date photometry. But it does seem interesting that Juliet, the sort of innermost moon, has a slightly distinct spectral shape. But really, the similarity is the most striking thing here. They all look like these water-rich KBOs. Let's actually plot a few of those water-rich KBOs from before to compare. And I've taken 2 sort of end members of this water-rich population. One is a hot classical KBO, which are sort of situated at 40 AU. They have slightly eccentric inclined orbits. And you can see this, very prominent, very sharp Fresnel peak at 3.1, very unlike what we see on Puck. It has also a CO2 feature, and it has deeper 1.5 and 2 microns. So perhaps it has just more water ice, though its 3 micron depth overall is lower. And another thing we can plot is to look at a centaur, which is a dynamically excited Kuiper belt object, something that has been kicked well within the orbit of Neptune. And this one is kicked in with a perihelion at 20 AU. So thermally, it seems like perhaps a decent analog to the Uranian inner satellites. It's sort of at a similar-ish temperature. So we can sort of remove that effect from the spectrum, but it looks quite different. It has a much steeper, redder slope seems to have even less water ice. And typically, what we see with these water-rich objects is that when they have a bit less water ice, they tend perhaps to be a bit redder, sort of ongoing work. And all of them seem to have relatively similar amounts of CO2, which indicates some sort of common trapping mechanism. I don't quite look the same, and sort of that's the thing we're still investigating, looking at what is really the difference between Puck and these objects. And that'll involve a lot of modeling going forward, potentially, and some thought about what are the different processes that these objects actually experience. Puck, of course, because of its proximity to 12 other moons, and because of the gravitational focusing of Uranus and all the objects that are flying around in the outer solar system, is experiencing a lot more collisions than any of these Kuiper Belt objects. So taking that into account is going to be important in really understanding the spectral differences here. And so the final component in our spectrum is the observation of the rings. We have, again, there's seven views of the ring here. And combining them, we can extract a pretty decent spectrum of the ring. We have, again, we can map sort of pixel by pixel all these components, and that's ongoing work. But we do see the same Fresnel peak, we see the same CO2 absorption, and we see potentially hints of a 3.89 micron absorption, which people have attributed to a whole variety of things, anything from sulfur compounds to carbonates, all of which should have, other features in the near infrared. So this feature alone is not diagnostic of anything. I'm not going to claim a composition in the rings based on this relatively minor feature, but it does seem to appear in every dither when we map the composition of the ring. And so what you see on the bottom sort of panel is the crude method of mapping used here. I use some pixels at the faint dark line and subtract sort of the continuum, which is at the blue lines, just to sort of map and see, is this a real feature or is there just a lot of noise? And if there's a lot of noise, we should generally see, very bright pixels along with very dark pixels. But at all of these features, we see generally some bright pixels standing out. And here's the ring spectrum plotted against Puck. The pixels used for this ring shown on the left here is the red stars, and the green stars are used for the background subtraction. Essentially, what we see is that the ring does not really look like Puck or the other satellites, which are all relatively similar to Puck. Has a lot less water ice, which you can see by it having no 2-micron feature. In fact, the lack of a really distinct 2-micron feature in the ring was known. I think this is Catherine DeClear's work from 2013. It was shown that there's really not much of a 2-micron feature. There is a Fresnel peak, and there is a 4.5 micron, this sort of broader shape to the sort of farther part of this infrared spectrum that's indicative of small amounts of water ice, but there isn't really a signature as deep as you see on Puck. There's no really broad, like large 2-micron feature. There's no really deep 4.5 micron that is typical of a larger water ice abundance. And overall, the shape of the 3-micron feature is a bit different. You have this sort of shallower slope as you go from 3 to 4 microns. That is very different than what you see on Puck with this relatively sharp 3.6 micron. The ring does look distinct, less water ice, and perhaps that's not unexpected. As you go and move in closer to Uranus, you encounter the Roche limits for density of 0.9, density of 1. And so you should expect to see some kind of segregation of material, whereas as you move closer in, you should see denser material. And what the ring perhaps looks more like is it has perhaps some abundance of maybe a hydrated component to it, hydrated minerals, less so than on Puck. So perhaps that is the difference. And we'll take a look again at that when we look at the Neptunian system. And the Neptunian system was the sort of shocking result out of our program. What we see and what my co-author Riley is working on, she's the one sort of leading this work, is the very clear detection of this 2.7 micron phyllosilicate band on the satellites of Neptune. These satellites don't really look like anything else we've seen in the Kuiper Belt spectrum. Vaguely, they do maybe resemble a bit the sort of water-rich bowl-type KBOs. But if you look at the 1 to 2.5 part of their micron part of their spectra, they totally lack any hint of the water ice overtones. They do not have this sort of broader bowl shape at the 4.5 micron region. They sort of just have a slight downward sloping continuum. And they do not have any evidence of a Fresnel peak, which is typical of exposed water ice facets. There's really no water ice that we see on these surfaces. There's a hint of CO2 at Proteus, but almost no hint of any CO2 on Larissa and Galatea. So these moons look very depleted in their volatiles, unlike almost everything we see past 10 AU. And the key sort of feature that we've just not seen before in the outer solar system is shown by the dashed line with the exclamation question mark at 2.7 microns. And that to us looked like, this two-component model. You take the spectrum of Proteus, which is this 400-kilometer large body, and add to it some hydrated minerals, and you get the spectra of Larissa and Galatea, which are closer in. Interestingly enough, Proteus is right outside the synchronous rotation rate for Neptune. Larissa and Galatea are inside. So it almost seems the story seems to put itself a bit together here. Proteus looks like it has some hydrated mineral component. In fact, if you go back and look at the spectrum of the ring here, the overall shape of this 3 micron, this rapid downward slope, and this sort of slow rise back upwards from 3 to 4 microns looks a lot like Proteus. Which is telling us there's some similarity to this outer solar system hydrated material. Whatever is causing this 3 micron band, whatever is this sort of hydrated component in it, is probably pretty similar. And then at Larissa and Galatea, you have this addition of the phyllosilicate band, which means that there had to be some aqueous alteration, which is not something you typically think about at distances of Uranus and Neptune for small bodies. These Larissa and Galatea are around 200 kilometers in diameter. So these are not bodies that have experienced differentiation from their internal heat. They're just simply not big enough. So something has had to happen to them. Something about the early history of these bodies had to enable them to be aqueously altered to show this phyllosilicate band. And one trick that Riley came up with here is to take the spectrum of Larissa and divide by Proteus, which allows us to fully isolate this 2.7 micron band. Again, we don't really see it on Proteus. We just have this downwards slope into the 3 micron band. Whereas at Larissa, we have this very, very sharp sort of downwards cliff. And if you divide Larissa by a slightly rescaled Proteus to just match the overall depth of the 3 micron band, what you get is something that looks very classically asteroid belt-like. Anyone, who's looked at the spectra of hydrated minerals should immediately recognize this very distinct check mark-like feature, which is very, very typical of hydrated minerals in the asteroid belt. Not something we would have ever expected to see at Neptune. This was a totally unexpected result for us. And if we plot various range of chondrites, typically, CM chondrites are considered to be something that is an outer solar system-like material, we find that dividing Larissa by Proteus gives us a decent match to some of these chondrites. Still working on, what is exactly the best match. Some of these things that are more carbonaceous and that have a higher abundance of carbonaceous material tend to have this upward slope in the infrared from 1 to 5 microns that doesn't quite match what we're seeing on Larissa and Proteus. If you just ignore the 3 micron feature and draw a straight line, that straight line is a pretty good fit to what's going on in the spectrum. They're not too red. And so some of these carbonaceous chondrites are not as good of a match. This CM1 chondrite seems to do an okay job as well. But really, it's this distinct absorption, very sharp downwards spike at 2.72 microns. That is just screaming to us. They're phyllosilicates on Larissa and Galatea. It's probably the first detection of phyllosilicate material past Jupiter. Recent work by Ben Sharkey found phyllosilicate hydrated material on Himalaya, which is an irregular satellite of Jupiter. But past that, there's not been any detection in any of the small body spectra we've seen, and we have over 70 Kuiper Belt objects now with James Webb. Nowhere do we see this sort of 2.7 micron feature. So this has been a shock. Additionally, something we're currently working on is trying to tease out and see if there are any hints of ammoniation. Typically, when we think about phyllosilicates, one of the things we think is Ceres, right? This body that's just abundant in phyllosilicate clay material, and what we are trying to search for is, if you look closely at the spectrum of Proteus, there is this little divot at the 3 micron range, sort of 3.09, 3.08, 3.07. And that is often associated, if you look at the plot on the right, with the more ammoniated material on Ceres. You see that at 3.07 microns, there is an additional divot, and that has been attributed to ammoniation in the phyllosilicate material. And it would be interesting if we could actually more confidently detect that on Proteus here. One hint we have of that is again, when looking at the ratio of Larissa and Proteus, if we look at sort of the deviation from the flat line continuum, we see at 3.07 microns a spike. So interestingly, at Proteus, where we don't see as strong of a phyllosilicate band, even though we think that this weird, very straight downward slope is still indicative of some, perhaps, presence of some hydrated material, there may be ammoniation. And maybe some of that is due to collisions with Triton, then having dust that accumulates in some small amounts and mixes into Proteus, Larissa, Galatea, and there is some ammoniation known on some ammonia compounds known to be on Triton. But otherwise unclear if we see this band, but that would be a good additional compositional peek into what's going on with these bodies. And finally, we can compare the rings in both Uranus and Neptune. At Neptune, when we look at the rings, we see just a very, very clear absorption at 2.7 microns. Perhaps if we think about the 2.7 to 3 micron ratio, the rings have the greatest abundance of hydrated material in the Neptunian system, more so than even Larissa does. And it looks much more of a hydrated mineral component than the Uranian rings. But again, the Uranian rings do have this very gradual slope from 3 to 4 microns, and so perhaps they also have some small amount of the hydrated mineral components, some small amount of silicates that are hydrated because of the similarity to Proteus and the sort of way they look distinct from Puck, as shown before. So the Neptunian rings are still a data reduction challenge. They're quite faint and dusty, but we have 14 total dithers on the rings. So hopefully by combining all of them, this is just 6 dithers combined so far from Larissa. By getting the rest that are from Galatea, we should be able to get a much cleaner spectrum of the ring and see if that absorption around 3.4 to 3.6 microns is real. Can we actually see any of the organic components in that spectrum? So again, if we just look at the collection of these bodies, right, the ring at Uranus looks a lot more like Proteus, as I was just mentioning, and Puck looks distinct. Puck really looks like just Kuiper Belt material that was transplanted, somehow collided with, and left there at Uranus. So now I want to turn towards the dynamical picture of what's happening. Like, how do we actually explain these spectra? Like, what have we observed so far, and how do we actually explain it? What we've seen so far is these phyllosilicates at Neptune, and then by contrast, that the Uranian inner moons look like Kuiper Belt objects, that the Uranian ring doesn't look like its moons, and that you have more CO2 at Uranus, paradoxically, right? You have this volatile compound that, you have more of at Uranus than at Neptune. So that is also an indicator that at Neptune you have had to have much more thermal processing, that these moons in their early history had a lot more exposure to some kind of high heat in order to get the aqueous alteration that you see on them. Um, so what are the physics that are actually happening here, right? The first thing is collisions. Collisions are common to all of these moons. They experience collisions between each other and from external sources. The inner satellites are definitely going to hit each other because of the slow interactions with their host planets, the sort of tidal decay they experience, interactions with each other. They do encounter mean motion and inclination resonances with each other, and they might excite their mutual eccentricities and cause eventual collisions with bodies. I mean, when you have 13 moons at Uranus, they are bound to hit each other, and dynamical lifetimes of that system before a mutual collision have been estimated to be around 10 to 100 million years. Then the 4.5 billion years we've had of solar system history, these moons have almost certainly hit each other multiple times and reaccreted multiple times. And the other thing to think about here is collisions with the Kuiper belt, right? You have objects that are being gravitationally focused in towards their host, towards the Uranian-Neptunian system, and they will hit Proteus, they'll hit Puck, and there are, estimates from folks like Kevin Zonley and David Nisvorny has updated them that show that these moons are not stable to even external collisions. They have been catastrophically collided with once or maybe multiple times throughout their history. And there's just a lot more impacts than we see in the relatively pristine Kuiper Belt region. So these collisions are what is also responsible in part for producing the rings. Sorry, there's a whole abundance of different various types of rings. At Uranus, we see the more water ice abundant. At Neptune, we see the dustier, and now, as we know, phyllosilicate-rich rings, this hydrated ring material. And so the cycle of ring to a satellite, satellite to ring, is probably the dominant driver of the physics in these bodies. And so how do we combine the physics with the composition? And the analogy I kind of want to use here is the ship of Theseus, right? You can talk about Puck or you can talk about Proteus as some object that has existed for a long time, but the just sheer amount and number of collisions between these bodies means that this is probably not true, right? If we take a primordial satellite, think of some time, let's take the Neptunian system, some time right after Triton is captured. You have the replacement of the planks of the ship slowly with new planks. You can rephrase that process in our context as collisions. They will take chunks off the body or catastrophically destroy it and then reform into new bodies. And very early on, right after the capture of Triton for Neptune, if you have a regular satellite system, the timescale for collisions is very low. It'll be something on the order of some 1,000 years between satellites if you assume a relatively rich initial regular satellite system that had, maybe the number of moons that Uranus did. And then the question is, how fast out of this material that you take off these ships, how fast does it then reaccrete? What is the sort of recombination of the original ship into a new ship? And this accretional timescale is very fast. Once you form this ring of material, you should be reaccreting into small moonlets relatively fast. You should form, if you have a very massive debris disk formed from the collision of take Proteus, it's a 400-kilometer sized body. If it catastrophically at any point in its history collided with some other body, and then get a debris ring out of that material, you should reaccrete into some larger object on very rapid timescales. And so this process of you have a primordial satellite and you have a primordial satellite system and you remake these satellites into new satellites, this should be very fast. And the final sizes and orbits that you get are not really representative, perhaps, of the original size. And this is almost certainly true in the Uranian system, unless the capture of these objects or the appearance of these objects was relatively recent. Unless that's the case, they have had to be reformed, reaccreted many times. Though you aren't losing all of the material, right? In this process, you could say, okay, well, you form a debris ring, maybe some of it subsides onto the planet, but just the Poynting-Robertson drag and all the material that's lost is relatively slow. So overall, you should reform this material into new bodies, but some of it will be lost, not too much. And so the other final physics that goes into this problem is looking at the Roche limit. And this is a great plot by Mattis from a 2014 paper that shows the location of the moons of Uranus and Neptune relative to, and the location is translated into Roche limit density, the critical density at which an object can be held together by self-gravity. Given a certain density. And so if we look at the objects that we have and the minimum density that they need to have to hold themselves together, Larissa and Galatea are about the same distance as Portia. Proteus is much farther away. And unfortunately, even though we have this notion of the Roche density, only for Galatea can we say meaningfully that it has to be probably not fully composed of water ice. Even so, it's around a Roche density of 0.9, so we can't confidently make that statement still consistent with being, would be consistent with being a chunk of water ice had we not known that it's not that. So only for the innermost moons of Neptune do we know that they must be really made out of some rocky material. But overall, what Matt did propose is that the innermost moons of Neptune have to have significant material strength. In general, the likely hypothesis was that the material strength at Neptune was higher than for the moons at Uranus, and that seems to be confirmed by our detection of these hydrated minerals, right? These hydrated minerals likely have a lot more cohesion than just granules of water ice, some rock, some carbonaceous material, and some CO2 that is cobbled together into 100 kilometer to 60 kilometers, even the 13-kilometer size body we observed. So how do we put this all together? Well, what we want to think about is what is the origin of these satellites, and what does that origin then tell us about the evolution of these systems? So the first hypothesis we can think about is in situ formation, right? What if these bodies just formed where they are and they've been in place? Well, the collisions between themselves and with Kuiper belt objects sort of are a strike against that. However, we do have Proteus. Proteus is 400 kilometers. It does show some potential evidence of geology. It was resistant to this very large 230-kilometer size crater, which is its only known geological feature, the Pharos crater. So Proteus could hypothetically be a remnant original body. So let's say that at Neptune, there's some plausible evidence that you formed some of these bodies in situ, but definitely not at Uranus. I mean, these bodies have been pummeled and destroyed over and over again. What I want to think about for Uranus instead is a hypothesis inspired by work by Kegros et al. 2025, who look at the formation of Phobos and Deimos, and what they suggest is that Mars will shred an asteroid as it comes in, form a ring of material, and then recreate it into the moons. And I propose that perhaps something similar happened for Uranus. Perhaps you took one of these water-rich KBOs, perhaps an initially 300, a 400-kilometer size body, and out of it you shred it and form a ring of material that then accretes into Puck, the other 12 moons, and the ring itself. And in general, at Uranus, you have a lot less mass that you need to explain than at Neptune. If you wanted this mechanism to work at Neptune, you would need a lot of mass. Proteus is a 400-kilometer size body. I think alone it is already almost as much mass, or probably more mass, than the entirety of the inner part of the Uranian system. But at Uranus, shredding one of these relatively generic 300 kilometer, 400-kilometer size KBOs, water-rich one, seems like a plausible explanation for what happened here. The only sort of strike against this argument is perhaps why is all the material the same? Why has this happened only once? And perhaps each time that you do this, each time you have one of these encounters and you shred an object, you erased most of the history of the previous encounter. And the last encounter, you had a lot more encounters happen early in solar system history. And so simply what we're seeing is this last encountered Kuiper Belt object that was shredded at the Roche limit and then formed these moons and rings. So we have perhaps a hypothesis for Uranus, less so for Neptune. Um, and sort of what are the lessons we can take away? Of Neptune, I think our best hypothesis is that these small satellites are some iteration, some nth generation of that original regular satellite material that has been very ground up and recreated into uh, sort of these nth generation bodies. You had Triton get captured. It ejected most of the regular satellite system. Maybe much of it collided with each other, and you got these inner satellites that are made out of that very collided, very heated material. And that would help explain why there's a general lack of CO2 and why there's this hydrated, high temperature material, because these came from regular satellites might have had enough time to start differentiating, that had enough heat of accretion, and that then through catastrophic collisions had enough additional heat to form chondritic material, essentially. And what this tells you is that you do have chondrites forming, throughout the solar system. Now we have evidence of this sort of CM-like material out at Neptune. Just from, spectroscopic evidence, we have this very abundant 2.7 micron, this phyllosilicate material. So, perhaps this is evidence that the catastrophic evolution of the Neptunian system following the capture of Triton is what gives you Galatea, Larissa, and Proteus and their very volatile, depleted compositions. At Uranus, I think the best explanation is that the small satellites are captured Kuiper Belt objects that have been shredded at the Roche limits, and you get this ring of material that, outside the outwards of the ice Roche limit, 0.9 grams per cc, you get the icier bodies, you get something that looked more or less like the original body. Uh, you get what looks like Puck, you get what looks like Portia, which all look like these water-rich KBOs. And then the rings do look different because they are made out of denser material. But perhaps not, perhaps just by virtue of Uranus being out at the outer solar system, you could have a convergent evolution of material, and these small satellites simply look like water-rich KBOs because water-rich KBOs are flying around, and maybe Uranus is not entirely distinct in maybe its interior composition from these objects. Planetesimal accretion and combination of planetesimals into larger and larger bodies is, one of the mainstays of how we think planets form. So perhaps it is not too surprising, would not be too surprising if it were true that these moons simply were a result of that product. But because of the collisions and because of that physics, it does seem likeliest that the small satellites at Uranus are captured KPOs. Does seem like our current best explanation. So I will leave you with that. Any questions?
Right. Thank you, Matthew. Please put your clapping into your screen there. Thank you so much. That was a great talk. So much information in there. Please, if you have questions, feel free to put them in the chat or raise your hand and I can call on you. I see we already have something in there from Matthew Hedman. Anything to say about Nereid?
Nereid? Yes. So Nereid, I think is this is going to be my sort of paper I'm working on right now. Nereid is probably, in my opinion, an initially regular satellite of Neptune. Its composition looks like absolutely nothing else that we've seen so far. It has a very uh, blue slope, but then in the sort of farther infrared at 3 to 4 microns, it has a very sharp upwards sort of behavior at 3.6. So it has a very water-rich composition that doesn't look like any Kuiper Belt object. It doesn't look like Phoebe. So because Nereid, I've done the comparison with taking the VIMS part of Phoebe that has the highest water ice abundance and comparing it to Nereid. They just don't look the same. So compositionally, I think Nereid is very distinct from everything else, and it might be this surviving regular satellite. But that's a different story that I felt was too long and complicated to explain to include here. But we can talk more about that later. I can show you its spectrum.
Right, we have a question from
Yeah.
Riley. Go ahead, Riley.
Hi. I'm curious on
Mhm.
some of the spectra of Juliet and Puck and Portia. There is a little dip that looks like it's at about 2.97 micron. Is that like just a bad pixel in the data, or is that looks like ammonia?
It could be. Again, I'm, with all these reductions, all the scattered light, I'm not so sure what is going truly correct, but it could be ammonia. So I think for Puck, I should check every. I think the what I need to do is check every dither individually and check that it's there. The fact that I didn't really see this like little divot on Portia made me skeptical, but perhaps it could be. And it's also slightly different on Puck, like if you just draw a line downwards, slightly different than a Juliet. So I was worried that it might not be real, but it definitely is worth seeing if ammonia is there, right? We are thinking about it on Neptune, so why not Uranus, right?
Okay, cool. Thank you.
Yeah.
All right, we have a question from Heidi. Go ahead, Heidi.
Hi, thanks. Awesome to see such great spectroscopy. And I totally expected to see the phyllosilicate band, but I did not expect to see it out in the outer solar system. Planning that
Yeah.
for the asteroid belt. So that's very amazing and cool. My question is, I just need you to help me understand
Yeah.
how you're thinking that the Uranus moons could be primarily captured Kuiper Belt objects, but not the Neptune ones, since I would have thought there'd be a lot more opportunity for
Right.
KBOs out at Neptune. So could you help me understand that?
Right. So for me, the argument, that is what worries me in my argumentation here. But I think that there's just so much more mass in the inner Neptunian system. It's much harder to explain it from being purely captured Kuiper Belt material to have just, I think, that much more mass than at Uranus. And just the compositions are so distinct. I don't quite see why you would capture stuff at Uranus and it not have quite the same hydrated mineral properties that then you see at Proteus. I think something much more catastrophic had to happen for you to get the phyllosilicate bands. And the only way I think we can get that is by having this early event happen, the Triton capture, destroy the regular satellite system, really grind everything to bits with high temperature material colliding to make even more high temperature material. So I think you have to have an initially relatively heightened temperature for this composition to appear. What I think needs to be done is a more thorough dynamical investigation of what is the probability that you will actually shred a Kuiper belt at the Roche limit. There are people who are working on this for other systems, and I hope to maybe work with them or try and to do this experiment myself and see what the probability is of actually shredding a Kuiper belt object in this way. I think that'll be the key to answering your question.
Thank you so much.
Yeah.
All right, we have a question from Shosh Cole. Do you have JWST spectra of Miranda?
Yes. I think my co-author Riley is working on that one. It generally looks like the other Uranian satellites. Decide not to include here because it is, very differentiated body, very different from the sort of rough surfaces we see even on Proteus. So I felt it's more of a regular satellite than an inner satellite in that sense. But yeah, it generally looks like the other big Uranian moons.
All right. Well, if you come up with some additional questions, again, feel free to put it in the chat. For now, I'm going to transition to Jody. to talk about our community news.
Sure. All righty. Yeah. And Matthew, really incredible presentation. I particularly loved all of the spectra. So that's incredible. Okay. Yep. So usually in these telecons, we have just a few minutes at the end to throw up. Let me see the share. There it is, to throw up this slide. On the community news, this is just sort of generally things going on in the ice giant systems community. I'm hoping everyone can see this. And what I'm going to do is I'm going to like copy paste this kind of grossly in the chat if it'll let me, just so that you all can click on the links. And so hopefully that worked. Yeah, I think it worked. All right, great. And so what we have here is, of course, next month, we have another Ice Giant System seminar series talk. This one's going to be by Dr. Susan Benecke, I believe, Benecke. And that one is observations from of Uranus and Neptune, I believe, from opportunistic observations from New Horizons. There's also an APL postdoc position on Uranian moons, so that's particularly relevant to this community here. That one is due in about a week, though, so make sure you get those submissions in. Also due in a week, the DPS prize nominations, and then a few weeks after that, the DPS EPSC abstracts are due. That's a little earlier than it normally is, especially for DPS, mainly because this is joint with EPSC. That meeting is going to be in Finland, I think, in September, and so just note that that's kind of an early abstract deadline there. OPAG was delayed just a couple months to June 3rd through 5th, but it now has a formal date. It's hybrid. I believe the website isn't quite up yet, but that link should still go to whenever the website is live. And then Matt Hedman and Tracy Becker wanted to kind of plug this Uranus rings and small moons working group. Email them if you're interested in getting more involved. And Matt or Tracy, if you're online, if you have more things that you'd like to plug on that, feel free to speak up.
Just to say, we're happy for anyone to be involved. We're just trying to put together what are the big science questions on rings and small moons to work on. So feel free to send us email.
Very cool. Thanks, Matt. And then finally at the end here, you've got a community source list of people that are actively looking for PhD students. And so if you are in a bachelor's or an MS position and you're looking for a PhD position, check there. And then if you are looking for a PhD student, go to I think it's the second website, or maybe I have those flipped, but either way, check out the links so that you can look for PhD opportunities. And then with that, I'll pass it back over to Mallory. Thanks, y'all.
All right, that covers it. Thank you again so much, Matthew, for your wonderful presentation. Thank you all for joining. If you're interested in giving a presentation, feel free to reach out to myself or Jody, and we can get you on the schedule. And everyone have a great rest of your day. Take care.